Okay. Wow, Chloe. Wow. What a brown nose. Hey, put your names in. Yes, I want your actual names. No, I do not want nicknames. Yes, I want your actual name because I go back and I look at them and I need to know who said what.
Abort.
Abort.
Just do your entire
Check it. What's your name?
Yeah, put my whole name first, middle.
Oh, I spelled
Two more.
Coming in hot.
You heard me?
One more.
New Zealand? You went to New Zealand?
No, it's just the name of the shirt.
Okay, moving on.
So do you want me to say?
All right, so we're going to talk about the structure of the Earth and play tectonics theory and how it works. Your head is probably right in the way. You can.
Is it?
Yeah.
I'll move the camera. Okay.
Can I move?
All right, so we're going to talk about structures of the Earth. You've done most of this. This is a review and also a way for me to check and make sure who knows and understands what, so that we can reteach as we need to make sure you're getting the things the way that you need to.
It looks like
Okay, so the three major parts are the core, the mantle, and the crust. We have things like the upper core and the lower core, or the solid core, the liquid core, the upper mantle, lower mantle, the lithosphere, and the asthenosphere. We talk major structures. We've got core, mantle, and crust. But you also need to know some of those substructures. Okay, the crust, this is where we live. We have either the continental crust or the oceanic crust. Now if you look here at the bottom, our continental crust is much thicker than our oceanic crust. Okay, our continental crust is less buoyant than our oceanic crust, which is what causes our oceanic to sink beneath our continental. And our continental crust is generally much older than our oceanic crust, because our new crust is made at diverging boundaries in the ocean. Questions on that? You need to understand those differences between oceanic and continental crust. This video will be on the website as well.
Wait, all of this will be on the website?
I'm going to post this video on the website.
Wait, this? Everything?
Yeah, and it'll have this, and it'll have me talking, and it'll have this conversation we just had. All of it.
Wait, can I be in your video?
You are now.
Yeah.
How do we know what the Earth is made up of? So, if we, let me see if I can find my basketball real quick.
Whoa, you play basketball?
You used to be pro Keegan.
Oh, really?
No.
Back when?
Okay, anyway, if we take a basketball, I don't have it easily accessible, and you stick a Band-Aid on the surface of that basketball, the thickness of that Band-Aid compared to the size of the basketball is about the same thickness as the crust of the Earth is compared to the whole size of the Earth. So it's very, very, very small compared to the whole size. The crust is not very thick at all. But we as humans have never drilled all the way through that crust anywhere on the Earth. Okay, so
I have a question.
yes.
So, I've asked this question before, not to you though. So, if you drilled a hole, like here, if you drilled a hole and you went all the way to the other side and you jumped in it on this side, what would happen? Would you just go and then come back up?
You would die
Or would
halfway
you just,
through.
You wouldn't fall all the way through.
No,
You'd
because
get stuck
the
in the
core is
middle.
so hot. So
Here's what would happen, and I'll tell this in 20 seconds. You fall all the way through and then you go back down, but you'd be dead before you got to the middle the first time.
I mean, that's all right. That's
Okay? And you wouldn't be able to do
That's
it.
all right.
Yeah, because the pressure would just
Okay.
squeeze you.
Back to the topic at hand. Being as we've never drilled to the mantle, never been to the core, never done any of those things, the question is how do we know about them? If we've never been there, what tools do we use to figure out those things? How can we say there's a liquid core and a solid core? Eric? Okay? Sonar tells us the depths of the ocean. It can tell us a little bit about the crust, but we use something very, very similar. Okay? We use the waves from earthquakes and how they pass through the earth to tell us the information about them. Okay, let's quickly go over the types of waves that we have. We've got primary waves, which happen when? When an earthquake happens, primary are the first waves that come. Okay, what type of waves are they? Longitudinal or transverse? Longitudinal, right? They go like this. Okay, our next type of wave is what?
Secondary.
S waves or secondary waves. They happen second. Okay, what type of wave are they?
Transverse.
Transverse. They go like this. Okay, so we've got primary waves that are longitudinal, and we've got secondary waves that are transverse.
Bless you.
Which type of wave can travel through both liquids and solids?
The longitudinal.
Longitudinal go through both liquids and solids. Transverse or secondary go through only what?
Solids.
Only solids. They do not go through liquids. Okay? So if we had, for example, an earthquake on this side of the earth, and we had somebody over on this side of the earth watching for those waves, okay, and we have primary waves that go through the earth, and we have secondary waves that go through the earth. And we know that primary can go through liquid and solids, but secondary can only go through solids. So if that earthquake happens, sends off both types of waves, the person on this side of the earth only sees primary waves. What does that tell us about what's inside the earth?
Liquid.
There must somewhere be
Liquid.
liquid somewhere, right? Because the primary and the secondary can go through solids, but the secondary can't go through liquids. Okay? So it's stuff like that that we use to tell us what the earth is like. And we'll do an activity that is in much more detail on that, and you'll actually be able to start to figure out about how big that liquid part should be from that activity. But that's how we do it. We use earthquakes as the primary tool that scientists use to figure out what the earth is like, because no one's ever been inside of it. Okay, so we're going to look at the theory of plate tectonics now. Okay, we started with what scientists first called continental drift. That the continents drifted on whatever was underneath the crust around. And we added some pieces to that and become more specific, and now it's called the theory of plate tectonics. Okay? So what happened first is you can notice that there are some pieces of our Earth that look like they might fit together like puzzle pieces. And that's where the first idea came together, that they had once been together and so they had drifted apart.
So at a time, if that theory is true, it would have just been one clump of land and then everything else is just water.
Yeah. Wouldn't there?
And our continents are still moving, so they will still come into different configurations in the future.
So eventually, the California will hit whatever's on this side.
If that's the direction that we're moving in. Eric?
So, like, far, way far into the future, it could just be like one big clump of dirt.
Okay. Yes, and there are simulations you can look up online that will show you historically where continents were and in the future where they're headed. Okay, so our crust is divided into 12 major plates. And these plates this motion causes these plates to collide, smack together, which causes these types of characteristics. So it says each type of interaction causes a characteristic set of earth structures or tectonic features. The 4 maps and 5 types of data that we looked at are those structures or tectonic features. And we've talked a lot about what type of stuff can you find in a convergent boundary, what type of stuff can you find in a divergent and a transform boundary. Those are the structures or tectonic features that happen because our plates are moving. Okay? So, what we want to start out with is a look at the 12 different plates. Okay, we can see that some are very large and some are very, very small, but they're all moving in some way, and those interactions cause things like earthquakes, mountains, trenches, volcanoes, new crust, subduction zones. All of those motions cause those types of features. Okay, what I want you to do is to put in your own words a definition of plate tectonics. Okay, so in the next 30 seconds, write in your best definition of the theory of plate tectonics. What is it? What is it about?
This is frustrating. I've tried. I yawn.
Mr. James,
What?
my iPad was doing weird and it like logged me out of it.
You have to log back in, and it'll take you to the same place. It didn't.
KGBRY. Okay, time's about up.
Wait.
I hiccup.
Wait.
Let's go back.
Okay, 10 seconds for the rest of you. Okay, here's one that somebody said. It's almost like states with boundaries. That's true. We've got all of these places that have boundaries. And where we're most concerned is the places that interact, right? The edges, the boundaries.
Yeah.
Okay, stuff that makes movements of the Earth. Okay, movements of our Earth's crust or lithosphere. Somehow those are getting moved around. Okay, some of the causes are, or the effects of that, plate tectonics are the reason we have mountains and other things on Earth. Okay, if those other things include earthquakes and volcanoes and trenches and ridges, that would be true. Okay, plate tectonics are when the Earth fit like a puzzle and they were once together but eventually they drifted apart from each other. They are still moving today. Plate tectonics cause earthquakes, mountains, and trenches.
So if you had to give one definition,
We will talk about one definition in a minute. Plate tectonics are pieces of the Earth's crust that move extremely slow.
That was mine.
Okay, they were once together and they moved apart, and they are the boundaries or places that define why there are some features on the Earth. Okay, so we're going to give a definition of the theory of plate tectonics. It's a theory that explains how the Earth's crust is broken into pieces and how those pieces move and interact to cause things like earthquakes, volcanoes, mountains, and trenches. Okay, I'll say it again.
Say it slower, I'm writing this.
You don't need this verbatim.
Oh, I need it, yeah.
Okay, so plate tectonics is a theory that explains how the Earth's crust is broken into pieces and how those pieces move and interact. Okay, and those interactions cause all the things we talked about: earthquakes, volcanoes, mountains, trenches.
did you say that Earth's crust?
Yep, Earth's crust broken into pieces, and the theory of plate tectonics tells how those pieces move and interact and what they cause. Okay? Okay, so what are our plate tectonics made of? Okay, plates are made of our rigid lithosphere. Okay? Remember our lab activity we did with the candy bars that represented our lithosphere and the properties that they had. If we warmed them up, they were more malleable. If they were cold, they would break more easily. They might have smaller pieces when we break them when they're cold. Same thing is true with our lithosphere. If it's old, it's colder. If it's warm, it's younger, and they have different properties at those different temperatures or ages. Yes?
So do we live in the stratosphere?
We live in the biosphere, which is right on the crust. Troposphere is above us. Those are the layers of the atmosphere. Okay? So the lithosphere is made up of the crust and the upper part of the mantle. Right below our lithosphere is the asthenosphere.
That's a funny word.
Okay? Asthenosphere is the place where our convection cycles happen. Okay? And that's what we're going to talk about next, is how do our plates move. Okay? So we talked about how there are all of these plates. So the guy who first came up with the continental drift, his last name was Wegener. Okay? One of his problems that he didn't have an explanation for what made the plates move. He just said the plates are moving. He had no idea why they were moving. He just said they were. So scientists have been working to come up with explanations of what causes the plates to move. Okay? Even this, plate tectonics theory is actually a pretty young and pretty new theory, like less than 100 years old. Okay? And so scientists are still working on trying to figure out and explain all of these things. This is our current best explanation of why they move. Okay? And we'll talk about two primary ways that plates move. Ashley.
What's the code again?
Kgery.
Kick a breathe.
Okay? So, the plates of our lithosphere are moved around by underlying hot mantle convection cycles. So everybody's eyes up here. You'll be asked to explain this in your own words in a minute. Okay? We know that the farther in the earth we go, the hotter it gets. So it's going to be hotter here than it is up here. Okay? And so our magma that's down here is heated up. And what happens to hot things? They melt and they rise. Okay? Just like when you're boiling water. The water at the bottom of the pot is hotter, it comes up to the top. Okay? Just like a lava lamp. The light's at the bottom, it heats up, it rises, it cools, it falls back down, heats up, rises, cools, all of that. Okay? So the same thing is true here. Right? Our magma down here is hot. It gets hot, it starts to rise. Okay? It comes up here, underneath the plates, starts to cool, drops back down. Heats up, rises, cools, and falls. And that creates these convection cycles. Now, as my arm is the lithosphere, and this hand is the magma, as it falls, it heats, it warms, it's going to push it along as it's moving. Okay? Those are called convection cycles in our mantle. That's one of the primary ways that our crust moves. The other primary way our crust moves is once we have a conversion boundary with a subduction zone, which is shown here and over here on our diagram. Okay? This is older crust. Previously we said oceanic crust or older crust is more dense. And we also on our structure and movement of the earth assignment, it talked about how dense things sink into things that are less dense. Okay? A rock sinks in water. Okay? That subduction zone is more dense, and gravity helps to pull it towards the center of the earth. So as we're going along, we have our convection cycles pushing our plates along. We get a subduction zone, and that continues to pull the rest of the plate along, pulls the rest of the slab along, which is why it's called slab pull.
Yes.
Okay? So our two primary things are convection cycles and slab pull. Caleb.
So what happens when eventually all of the crust gets pushed underneath and melted?
So if we are having two convection zones, right? We're separating here, we're getting rid of here. So what's happening in the middle, Caleb? And what would happen there? New crust. So it's like a conveyor belt of crust.
Oh, and then it just forms into the...
New crust, it gets older and older and older, more and more dense, more and more dense.
Oh.
Millions of years, it's just passing back and
So
forth.
we're never going to not have them late.
No, we will always have crust. Okay? Any clarifying questions on that? Nope. Okay. What two processes cause plate tectonics to move? Is it slab pull and volcanoes, mountains and trenches, trenches and convection cycles and slab pull, or earthquakes and volcanoes? What two processes cause our plates to move? 5 seconds to answer. 5, 4. Okay, let's take a look. Okay, most of you, 81%, said convection cycles and slab pull. We only had one person that said slab pull and volcanoes. Okay, so convection cycle, there's the movement of our magma pushing along or pulling our plate along with it. And then slab pull is once we have a subduction zone, that gravity pulls it towards the center of the earth and pulls the rest of the plate along with it. You will need to know those and be able to explain and describe those processes. Okay, draw a convection cycle and include some indication of temperature. I'm going to give you 2 minutes.
Mr. James, my
What?
name's not working.
Log back in.
Mine just did the same thing.
ADRY.
I don't know.
Should take you to the exact same page. Okay, draw a convection cycle, including some indication of the temperatures and how that will make your plate move. You could include things like specific types of boundaries to show where we would have a divergent boundary and where we have a convergent boundary. But you've got 1 minute and 30 seconds to do it.
Why?
Because I care about it.
This word keeps popping up when I drop it. Punch it. Base.
Okay, draw a convection cycle, include some indication of temperature. You can use a color, you can label it, whatever you need to do.
Oh my.
1 minute.
Did you get that near podcast connection?
Yeah.
If you let your computer go to sleep, you will have lost connection. You gotta log back in. What's a convection cycle? Okay, we just looked at several diagrams of them. 30 seconds.
Mr. James.
First did it, learn to floss it, so.
Mr. James.
First beer said, check, spend this over there, floss.
Let's retry.
Send, bam, got them.
I'll give you an extra 30 seconds.
Taylor, you caught me.
15 seconds.
No, I didn't. I'll just send them.
Okay, look.
No. Hot right there. What is it? Where do I see two?
Forgot to have the.
Okay, let's take a look at some of them. Okay, here's one that's showing hot. We have definite cycles, but we could use some indication of where it's cool. We could also use an indication of which way that's causing the plates to move. Here's one that shows the magma, where it's cool in our cycles. I'm not sure if these are subduction zones. Are these intended to be subduction zones, Brandon?
Yeah.
Okay, so we've got subduction zones, some arrows showing us which way that's moving and help us. Okay? We could also have a divergent boundary to show that we're splitting apart. Okay, so those are some tips, some things to add.
They don't have enough time to go into detail.
Okay? 2.5 minutes, plenty of time. Okay, here's an example of good where we've got hot temperatures and cool temperatures,
Mine's stuck.
but we could use some indication of the plate movement as well.
Mine's stuck.
Dun, dun,
Okay, here is one that shows hot and cool, and also showing a subduction zone and our plate. So that's good, it's showing there. One thing I might add, is a direction showing which way the plate is moving as well. Okay? Okay, this one's showing our cycles, and it's showing where it's hot and cool, and it's also showing some arrows of where our crust is moving.
Thank you.
Okay, pay attention, guys.
Okay, so
On the last one,
Okay? Stop talking while you're over there.
KGBLY.
Okay, so we're showing movements. Good. Okay, so you will likely be asked to diagram those things. This is in preparation. Okay? How do convection cycles and slab pull cause plates to move? Describe processes. How did convection cycles make plate moves? Plates move, and how does slab pull make plates move?
Really?
I was looking at this, thinking it was going to submit it and then just mix it live. Oh, I didn't know that.
Some of that.
What is Simpson mean?
Type of lettuce.
Type of lettuce? What?
It had to be that.
Are you?
And then what range on it or not? Range? That's right.
Where's the water?
Okay, 10 seconds, finish up your sentences, submit them.
Did your group
Waiting for one person, I think.
No group, yeah.
Okay, I'm going to say this as a general statement. If you're putting IDK or I don't know or whatever, that means you have some re-evaluating to do. You need to work a little bit harder to make sure that you're internalizing the things we're talking about. This video will be posted. That means you need to probably go back and re-watch the video. Go back and look at assignments again that cover this. Or come talk to me so we can go over it again. Okay? Part of this is for you to see what you know and what you don't know, and part of it is for me to see what you know and don't know. If you're putting IDK on stuff, you need to be changing what you're doing.
I didn't forget.
Okay, convection cycles and slab pull makes plates move because the motion it is going in and rubbing against the plate to travel in that direction. What do you mean by rubbing against the plate? Okay, can you give me an example? What do you mean? Where is it rubbing? Okay, if this is my convection cycle and this is my plate where it's rubbing. Right here, right? Okay, very good. Okay, it's the movement of this underneath it that's pushing it along. Brant?
It's also going when it goes like this.
Yep, so if it's going like this, it's going to be pushing them two different directions. Convection cycle is like a conveyor belt. The slab pull pulls the crust in as the cycles take it through transformation. I really like that the convection cycles are like a conveyor belt. Okay, somebody explain to me how crowd surfing works.
The people, you jump on the crowd and the people push you through everyone.
Okay, so they hold you up and they pass you along, right? Okay? So if our plate is like the person and our magma is like all the people holding them up, as the magma moves, it's floating on top of it and it's pushing the person along. Okay, so we can think of convection cycles kind of working like crowd surfing.
What will I put on a crowd surfing?
On what?
Making a hole. On a pole? I don't know.
Okay, you worked out in your head.
Stop, you're making it.
Okay, convection cycles push the plates forward into other plates. Slab pull then uses gravity to pull the plate towards the center of the earth at a subduction zone. Okay, once we have a subduction zone, that's the only time we have slab pull. Otherwise, all of our movement is from convection cycles. Okay, let's keep going. Okay, we want to talk about what happens at our plate boundaries. We talked a lot about this. This is a review and a checking. We've got three types. You've got to know the three types. You've got to know that we have divergent, convergent, and transform. And you've got to know what data we see or what characteristics we see at each type. Okay? Okay, what data do we find at transform boundaries? Okay, I'm going to walk you through this so we can get a little quicker at it. Okay, earthquakes. What do we see in earthquakes? Write that down. Do we see spread out earthquakes? Do we see them get deeper, or do we see them shallow in a line? Which of those three options do we see? Now I will say, some of you know the board is there. Don't use that as a crutch because it won't be there when you take your test.
Then we submit it to spell.
No. What happens with our volcanoes? Are they spread out? Are they in a line? Or do we not have very many of them? What happens with our age of our crust? Is it making new crust? Is it not making new crust? And last but not least, what happens with our topography? Do we have mountains and trenches? Do we have a ridge? Or do we have nothing special?
I don't know how to spell.
20 seconds to finish that one up.
Do we spin it now?
Yep. Once we've covered those 5 data types,
Wait, what other data? 5 only or 3?
the bathymetry and topography go together in geography. Trenches and mountains, that's bathymetry and geography. Wait. Ten, 9, 8, 2, 1, 0. Okay. So what we should have is we should see earthquakes spread out. We should see volcanoes spread out. We don't have anything special in our topography or bathymetry, and we're not making new crust. The tendency that people have when you're asked that question, because I've seen it through the whole project, is that you'll say, oh, they run past each other. Okay? We want the data. We don't want a description of what a transform boundary is, we want the data. When it asks for what happens at a transform boundary, what is the data, don't say they rub past each other. You've got to say earthquakes do this, volcanoes do this, geochronology does this, etc. Okay, so you've got a picture of a divergent boundary. We can see our convection cycles spreading those apart. We can also see that it's creating convergent boundaries on the other ends. Okay? If we see that on the Earth. If we've got divergent boundaries in our oceans, most of our convergent boundaries are on our coasts. That's where they're meeting up with other crusts. Okay, what data do we find at divergent boundaries? Do we see volcanoes? Do we see volcanoes spread out? A few volcanoes in a line? Or do we see volcanoes in a line? Earthquakes. Do we see earthquakes spread out? Do we see shallow earthquakes in a line? Or do we see earthquakes that get deeper? Topography and bathymetry. Do we see mountains in a trench? Do we see a ridge? Or do we see nothing special? And seafloor age. Do we see new crust or do we see not new crust? Making new crust or not making new crust?
And then most of the other ones are
Volcanoes and geography.
I don't remember what that one is.
Okay, 5, 4, 3, 1.
Watch.
Submit. Got it? All right. So, what should we have? At a divergent boundary, we should have creating new crust. We should have a ridge that gets shallower. We should have few volcanoes and
Earthquakes.
shallow earthquakes in a line. We should have
Oh,
those.
just put the line part, but I put shallow six. Does that count?
Yeah.
Yay! Okay.
Okay? As you see on your picture, most of our new crust is in the middle of the ocean, which means most of our divergent boundaries happen there. One of the very few places we have a divergent boundary on land is in Iceland. We can see that that boundary goes right through that island and that it's splitting it apart. We can see in that picture that we've got cities with these volcanoes right next to them where it's being split apart. Where do we find the most divergent boundaries? Along the coast, middle of the ocean, below islands, on tall mountain ridges, or Texas? Texas is not the right answer.
Where did you put the first psychology?
Live in Texas. Well, you shouldn't have started singing that.
Sorry.
What? Oh, yeah.
We could have more than one answer.
But there is only one.
No, you can't because it'll show up as no. Not answer.
Figure that one out.
No answer.
An obvious.
And not
I'm divergent. Kind of hurt.
convergent, not okay, let's take a look. Most of you said middle of the ocean, which is correct. Texas is wrong. Along the coast is generally our convergent boundary. All mountain ranges is our convergent boundary.
Oh wait, we don't have it.
Put tall mountain.
Okay, convergent boundaries. We've got 3 types based on our 2 types of crust. Convergent, convergent. Excuse me, continental, continental, continental ocean, and ocean, ocean.
Wait, what's ocean?
Well, we'll look at them. Okay, continental, continental. Our biggest place where we have that is the Himalayan mountains. Okay, they make really tall. No, this is an example. They make really tall mountains.
Oh no, I took a picture
Okay,
of the...
what data do we find at convergent boundaries? So, on our volcanoes, do we see volcanoes in a line? Do we see few volcanoes, or do we see volcanoes spread out? On our earthquakes, do we see earthquakes spread out? Do we see shallow earthquakes in a line, or do we see earthquakes that get deeper? And our seafloor age, do we see not new crust or new crust?
Put the T before the S. Whoops. So it's like crush.
And the last one, topography. Do we see nothing special? Do we see a ridge, or do we see mountains and trenches?
What's the pin?
The what? KGBRY.
It's buried.
There are mountains and
Oh, pressure. There.
Katie stands for environmental science. Yes, for her.
Okay, what do you do?
Environmental. Are you within your size?
I don't know.
Okay, still waiting for a lot of you. Submit. We walked through all 4 of them.
Trying to help.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, what should we have? We should have mountains and trenches, volcanoes in a line, earthquakes that get deeper, and not new crust.
Shallow to deep.
Earthquake.
Okay, so a continental boundary is the Himalayas. This shows us an example. Some of you asked questions about if we read runtime in reverse or runtime forward. Here's where the India landmass was 71 million years ago, 65 million years ago, 38 million years ago, 10 million years ago, and today it's slammed into that other continent, and that's built up the tallest mountains in the world. Here's the continental oceanic crust, which is our most common one, and what we have here that we should be very familiar with. Okay, lots of information on subduction zones. We've talked about melting plates that cause eruptions and volcanoes. We've talked about why we have earthquakes that get deeper. Okay, tell me what a subduction zone is. Video on the classroom website.
I'm gonna have to rewatch
What is a subduction zone?
I'm gonna rewatch it because I forgot what a subduction is.
Oh, it's up there. Okay.
I didn't know that. I forgot.
Submit, and I'll see you later.
Have a good rest of your birthday.
They-
I like the shirt. It looks nice.
Wow.
2 ahead, actually.